12.4. Last section that we're going to look at in this chapter is dealing with, now that we have taken a look at the graphs of our conic sections, what happens if we want to move them to a new location? So translation is a term for referring to a movement. And we're going to learn about what's called a translated axis system here. So in the diagram to the right, we have our normal coordinate plane, x and y. The red diagram that we see is we refer to as our translated axis system. And you'll notice that what we've done is we've taken our original origin, 0, 0, and we've picked it up and we've moved it. We've moved it to the right some value of h, and then we moved it up some value of k, giving me this new coordinate hk. And all this thing means the 0 prime, 0 prime. Prime is a way of denoting a new location for our origin. And so when a translated axis system is taking your original origin, moving it some values of h and k, and establishing a new position right there. So that's all that that is referring to. It's a little bit confusing, but just think of it as we're picking up our graph and we're starting over somewhere else, basically. And then we have these new points then. We have some point P in our normal rectangular grid, which is coordinate x and y. Well, now in this translated grid, we're actually going x prime over and y prime up. And so that's where those coordinates are coming from. So our translated system keeps our x-axis parallel to the x prime axis, and it keeps our y-axis parallel to the y prime axis. Now when we were talking in maybe in Algebra 2, you guys were referring to movements. This is along the same line of that. So it's no different, just some different terminology. All right, translation formulas. Here's where this whole idea of h and k comes in. So that h is either the movement left or right of our original position, and the k is either a movement up or down from our original positions. And that's what's happening here. So here in the first equation, we take our x and we refer to our translated axis as an x prime plus an h value, taking me back to the original x. Most often, though, we see it this way, where we have x prime is denoted by x minus h, and we think opposites. Kind of like when we were graphing parabolas back in the quadratic chapter, when it was in parabolic form, we had something that looked like y equals a x minus 3 squared plus 2, for example. What was happening in here is we were actually moving right. And that's what's happening between this function and this function. It's telling me how I have this relationship between this prime position and our normal standard position in our grid. So if x prime is equal to x minus h, then that means y prime is going to deal with the k value, which is the up or down movement. And I get y prime equals y minus k. So now what we're going to do eventually is anytime in one of my equations after I've rewritten them, if I get something that has y minus k in it, and we say write this as a translated system, that means we're just going to replace y minus k with y prime. So here we go. We take the same equations that we've worked with before, parabolas. We got circles in here because we're going to talk about translations of circles again. And then our ellipse and our hyperbola. So the same major components are there. X squared equals 4ay. But then we introduce these translation values. means I'm moving my graph now. So x minus h, according to what we just saw, that x minus h means we're moving right. H value. If it was x plus h, we would be moving left, however much h is. Same thing works with k. Y minus k moves up k. And y plus k moves down k units. So here you're talking about your new vertex. If we've moved hk units, our vertex now will be at hk, which means our focus for this parabola, this is one that is opening up or down. Our focus will have the same h value, but now our y component of this focus is going to be what the k is plus that a again. And that a, remember, is the distance between a vertex and our focus. Same thing applies for if I'm positive A, I'm opening up. If I'm negative A, I'm opening down. Same thing over there on the right-hand side for my left-right parabolas as well. So we run through all the different scenarios with each of our equations. Again, there's the circle. Your normal circle without any movement, again, was x squared plus y squared equals r squared. And then we introduce our translations of h and k in there. And we do the same thing for the ellipse. Nothing changes with the axes. The a's and b's are just a distance away from my center. So for wherever my center is, once I know that, I'm able to just work with these a and b values. And the same thing again with the hyperbola. Conjugate axis, transverse axis. All right, so there they all are. The whole idea of moving my graph around. So we have in our first example a curve that has the equation of x minus 3 squared plus y plus 4 squared is equal to 16. And this next part, we'll eventually be able to know where my origin has been translated because I'll be familiar, hopefully enough, with the equations to know what my h and k are. But here, I'm telling you what h and k is. In fact, maybe you do this. Directly above the given equation, you write the generic. Now, in that case, I see x minus 3, I see x minus h. Well, that must mean that h is the same thing as 3. And there it is. There's my h. But you'll notice for the k value, I have a minus a k, but here in the equation I have a y plus a 4. Well, that happens when we do this. Y minus a negative 4 is what y plus 4 is. And so this value is what my k is. All right, so they match. Now we're supposed to find the equation of the curve in the translated system. So what that means is our equation is not going to show this h and k value. Because we're going to take our origin, we're going to put it at 3, negative 4, and then we're going to write our equation as if that is the new starting point, new origin destination for this particular graph. Do we know what this kind of graph is? Well, I hope that we're able to see that it is x squared plus, which means it's going to be either a circle or an ellipse. I don't, again, I don't have any coefficients hanging out here in front. So if I interpret it as an ellipse, and I divide by 16, I get 1 over 16, 1 over 16 for x's and y's. B and A are the same length. That must mean this is a circle. So I have a circle here. So this is going to be modeling after my x minus h squared plus y minus k squared equals r squared formula. So r squared is equal to 16, which means r is equal to 4. All right. R is equal to 4. Let's draw a little sketch of what's going on here. So I've translated, I've picked up my original origin of 0, 0 has now moved right 3 and down negative 4. I'll get it right one of these days. There we go. It moved right 3 and down negative 4. That is now my new y prime axis and my new x prime axis. We're going to write an equation from there, assuming that's my quote 0, 0. And everything will be now in terms of primes. And so we go back to our translation formulas where we found out that we said x prime was equal to whatever x minus h is. And y prime was equal to whatever y minus k was. So that must mean in our situation that x prime is equal to x minus 3, and y prime must be equal to y plus 4. That must mean then my equation in translated system form would no longer be x minus 3 squared plus y plus 4 quantity squared equals 16. It is instead going to be x prime squared. It was a little funny there. X prime squared plus y prime squared. It kind of looks like an exponent of 12. I'm not intending it to be that way. Is equal to 16. So that would be the equation I'd have if this were my start point, or my new origin. I would be able to draw the same graph as the x minus 3, x plus 4 squared equals 16 by using this equation, but starting at that central point of 3, negative 4. So here's what the graph would look like. There it is. And again, that came from me having this graph. So I have this circle here. And I pick that circle up and I move its center to right there. Or I adjust the origin and I would get the purple. So that's what it means to write as a translated system. It's just we're changing whatever our plus hk things are into these prime values. Let's try another one. This curve has the equation of x plus 2 squared equals 8 times y minus 3. And we want to find the equation and identify the curve. All right, identifying the curve. Let's see. I don't see any y squareds. That means it can't be a circle. It can't be an ellipse. It cannot be a hyperbola. So we're only left with one other option, and that is our parabola. So this thing must have been modeled after something like this. Where I see here I've got this 8, that must be the same thing as my 4a value. And I've got an x that is moved to the left 2. So I have my x minus h is actually equal to my x plus 2, which is an x minus a negative 2. So that means my h is a negative 2. I've moved left 2. My y minus k is equal to this y minus 3, which means my k is equal to a 3. So I know that I've moved my origin to negative 2, 3. Again, we were given that information up here, but I want you to be able to take a look at the equation and see if you can find out that information without being given the origin. All right, so we have a new point of negative 2, 3. Let's see if I graph this right. There is my new origin of my translated system. And we're going to find the equation of the translated system. Well, it kind of sounds complicated, but it's really not that bad. Let's get the hang of it. We know that our x prime is equal to our x minus our h. So x prime in this case is equal to x plus 2. And our y prime is equal to our y minus k, which means our y prime is equal to the y minus 3 value. And now we just substitute those in. We substitute these prime values in. So x plus 2 quantity squared equaling 8 times y minus 3 would become x prime squared is equal to 8y prime. There's my translated equation of this parabola. So let's see if the graphs should be opening up. You have a vertex hanging out at that negative 2, 3 point. And there it is. Okay. What about, here we have been given equations in a different form. This is that generic conic form that we looked at back in section 1 with parabolas. It's ax squared, sometimes it had a bxy, but in this case we have no bxy value. We have cy squared and bx and an ey and f. And we're supposed to graph them from these equations. So it might help if we were able to rewrite them into a form that we're familiar with. So that is what we're going to do. But in order for us to do that, we've got to go back to the days of completing the square. All right, hopefully you'll remember the whole completing the square process. We'll try and highlight it quickly here in this first example. So we have another situation where I don't have any x squareds in this equation, just a y squared. It means I probably have another parabola going on. I have y squareds and y's, and I would love to complete that square so that I'm able to write that as a binomial square. The x, there's no x squared with it, so I don't have any completing the square work to do on that. So let's focus on the green y squared minus y, 8y thing. First thing we would do, if there was a coefficient in front of y squared besides 1, is we would factor that out. But there isn't, so we're able to just go right from here. And what we want to end up doing is we want to find what would I have to add to 8y and y squared so that I complete the square, meaning I would want to be able to rewrite it as something squared. Y minus something squared. Well, when we complete the square, we take whatever our b is, which is with our, not our y squared variable, but our just y to the first variable in this case. We take half of that, we square it, and that's what shows up here. So we have negative 4 squared, we get 16. Now, what shows up on the other side shows up over here is just half of our b value. That's what goes here. So this would be a minus 4. Now you can check it. Y minus 4 squared. Foil it out. Y squared minus 8y plus 16. That's what we get. All right, so we complete the square here on in the green section. Let's continue with the problem. So I would have right now y squared minus 8y plus 16. Maybe we do that a different color to see what's. And then minus 6x plus 4 is now equal to I added 16 on the left-hand side, so I have to remember to add 16 on the right-hand side as well. All right. Let's go ahead and get this, if we can. Well, we can. We want to get it into one of our parabola forms, and that means I'm going to get it into y squared equals something. So we're going to move everything over to the right-hand side of the equation and be left with y squared is equal to I'm going to move the 8y. Oh, wait a second. I don't want to do that yet. I'm jumping the gun. I don't want to do any moving until I have taken my y squared minus 8y plus 16 and written it as my binomial squared. So I want this first to be as y minus 4 squared minus 6x plus 4 equals 16. Now we can move everything to the right-hand side. 6x, what do we get over there? Plus 12, subtract the 4. All right, so it looks as though we have an h value, but the k, do we have a k value? We actually do. I look at what I have left, an expression, a binomial expression with an x term and a constant. And I will factor out a common factor here. In fact, you can always be safe in just factoring out the leading coefficient there in front of x. Sometimes you'll end up with a fractional constant remainder. Sometimes, like in this case, you end up with a 2. So if we pull out that 6, we get an x plus a 2. And this is equal to y minus 4 squared. So now, I am in the form of, seeing my h and k. A y minus k squared is equal to, well, 4a times, in this case, x minus h. So I can see that my 6 is equivalent to my 4a. And I get an hk of negative 2, 4. Negative 2, 4 is my hk. All right, forgot what we're supposed to be doing. Oh yeah, we're graphing. Graph into one of our standard forms. Okay, well, we're there. We have our standard form. And from here, I am able to generate my graph. Let's see, if we wanted to find our a value, we could do that. Our 4a is equal to 6, which means a is equal to 3 halves after I divide by 4 and reduce it. That can help me find my focus. So let's see what we would get here. Again, I'm going to have to split it into parts. There's the upper part. There is the lower part. And let's see if we actually started in the right spot. So we should have started at negative 2, 4. Yeah, there's where our vertex is. Our focus is going to be 3 halves away from there. That's what our a value is. So 1.5 away from there. That puts me right about there is my focus point. Again, we're talking about that distance right there is my a distance. All right, but we didn't need to do that. My directrix would be 3 halves on the other side. So my directrix is going to be negative 1.5 away. So what, somewhere over here? Something like that? Oops. Won't be tilted though, won't be slanted. So right around there. Negative a away. Yeah, another thing you could do, graphing, I have the luxury of having the software here, but you guys are probably going to want to just check t-table values. In fact, you are going to want to do t-table values. And again, your option, you can pick x's and find y's, but again, my suggestion is whatever is being squared, whatever variable is being squared, is probably the one I would put y values. In this case, I would put in my own, I'd pick my own y values, and I'd find out what my x's are going to be. And I'm going to do that with my, my normal, this equation right here is what I will use to generate my t-table values. All right, so there's completing the square, found our parabola. What about this guy? Oh boy. That is another parabola, but this time it's x squared, so it's going to be opening up or down. And I'll just walk you again through the completing the square process and then throw the graph up real quick. But if you want to try it on your own, you might want to pause right now and then check in just a second. So completing the square, we would take a look at those. Take half of 6 and square it, and I get a 9. I got to add that 9 to the other side. Now I'm going to take this and make it a binomial square. And then I'm going to isolate and get that by itself. It's equal to negative 4y plus 20. Then I'm going to see if I can show a k value over there on the right-hand side by factoring out the negative 4. Be left with a y minus 5. So I'm now in this form. X minus h, 4a, y minus k. hk is a negative 3, 5. 4a is a negative 4, which means my a is a negative 1. Right. So it wanted us to come up with our equation, and we went a little bit past where we needed to go equation-wise, but it wants us to come up with that. And then now we would graph this thing, and let's see, hopefully, give us in the right spot. Negative 3, 5 is where we want to be looking for our vertex. Negative 3, 5. There it is. We're upside down because my a is negative. Here's my focus, which means this would be my directrix. All right, and then I could, again, put my t-table together for this, using this equation. This time, though, because I was given x's is squared, I would plug in points for x and find out my y values. All right, there's that one. Transforming, now we get a little more involved here. We get x squared and y squared, so we're going to end up with ellipses or hyperbolas. Completing the square process now involves both for x's and for y's. Our constant, 71, is already on the other side. I don't need to worry about moving anything. All right, let's work in the green area. Completing the square here. Again, it's a little different. I've got a 9 as a leading coefficient of x squared, which means I want to pull my leading coefficients out. I'd be left with an x squared minus a 2x. I know you're thinking, why don't you pull the x out as well? Well, remember, for completing the square, I need to have an x squared term and an x term so that I can take half of the middle thing. So I get that, and I'm going to have to find out what goes there. And then, let's see, on the red, I'm going to pull out a 16. I'm going to be left with a y squared plus a 4y plus something else there. And then, I'm going to add those values do our thing. Negative 2, half of it is negative 1. Negative 1 squared is 1. 4, half of it is 2. Squared is 4. Got a little ahead of myself here. All right, now being careful what goes on the other side. Careful in this sense. Really what I've added on the left-hand side with the green numbers is 9 times 1. And I've added 16 times 4. So I got to be careful with that. When I pull out that lead coefficient, I have to remember to multiply that by this constant that we have found that completes our square. All right, now we can say 9 x minus 1 squared plus 16 y plus 2 squared is equal to 80 plus 64 is 144. Okay, it looks like we're going to end up with an ellipse here because I got x squared plus y squared. All right, we keep going now. Keep trucking along. And we end up with x minus 1 quantity squared over 16 plus y plus 2 quantity squared over 9 is equal to 1. And we can see our HK is equal to a 1, negative 2. So that is the center of our ellipse, 1, negative 2. What do we do next? Well, we go and we use these guys. a squared is equal to 16, so a is equal to 4. B squared is equal to 9, so b is equal to 3. My major axis is along the x, my minor axis is along the y. So I go plot these points. Now, these are points relative to the center. So when it says a is 4 or negative 4, right, plus or minus, I'm going to go from my center point to the right 4, to the left 4, and from the center point up 3 and down 3. And I can move this so I can get it to graph. Hopefully it's going to graph, right? I think I say that every time. There, look at that. Beautiful. So there it is. Translated. Identified a conic. Okay, it's an ellipse. We graphed it. Find the coordinates of any foci. Okay, relative to the original system. All right, so where are our foci here? Well, we know that they're going to be somewhere on this axis. So we can go find it. C squared is equal to a squared minus b squared. C squared is equal to 16 minus 9. So we're talking about c equal to the square root of 7, plus or minus that. Now again, that plus or minus 7 is a distance away from our new origin, or start point. So I'm going to be, what, negative 2 point something? So right 2 point something, left 2 point something, and there are our foci, F and F prime, for this ellipse. Now it says relative to the original system. So that's actually asking us probably to refer back to R00. So what would those coordinates be? Well, we would have F would have been starting at an x value of 1 and then adding to it a square root of 7. And then our f prime would have been starting at the same one, but now subtracting the square root of 7. And the y values for these would just be -2. So this is relative to our original axis. So square root of 7 is 2.6 roughly. So this is going to be 1 plus 2.6, 1 minus 2.6. So we have 3.6 comma -2. That's what our k value is. And that's where this point is. 3.6 -2. And then we're going to do 1 minus, so we get -1.6, comma -2. And that's where that point is. And those are relative to 0, 0. So those would be the actual coordinates of our foci. All right, again, here's where you can pause, come back and check in and see how you did. Let's see, I'm going to group them differently. 9x squared minus 18x plus 4y squared minus 8y equals 41. Factor out a -9. X squared plus 2x plus 1. 4 times y squared minus 2y plus 1 is equal to, run out of room again. All right, I'm going to worry about the equal to part here in just a second. I'm going to simplify this. -9 x plus 1 quantity squared plus 4 y minus 1 quantity squared is equal to, all right, so now we have 41. And then we added a -9 from the first complete the square. And then we added a 4 from the second. So -9 x plus 1 squared plus 4 times y minus 1 quantity squared is equal to 41 minus 9, 32. 32 plus 4 is 36. Then we will divide everything by 36. Get a negative quantity x plus 1 squared over 4 plus a y minus 1 squared over a 9 is equal to a 1. Well, that looks a little suspicious. We never really started with a negative x squared. Well, that's because we're going to switch them and end up with a hyperbola. There we go. All right, we know our h and k. -1, 1. We know a squared is equal to a 9, which means a is equal to a plus or minus 3. B squared is equal to a 4, so we are at plus or minus 2. We're going to have to find some foci, so now we have a hyperbola, which means we do a squared plus b squared this time. And we get 9 plus 4, so we get c is equal to the square root of 13, which is approximately equal to 3.6. All right. So let's first of all go back and identify where we're going to begin starting point-wise. We have, where's our HK? -1, 1. -1, 1. It's the hyperbola, so I will not be going through that point. That's just my center start point. Defines my new axis. I have an A, which is on the y-axis. My transverse axis is the y, so I'm going to go up 3 and down 3. And there are the two vertices of my hyperbola. My B is a 2. So I'm going to go out from there 2 and define my asymptote rectangle. then I'm able to put in my asymptotes. And then generate my graph, which I don't think, oh, that was dumb. Put it back. There we go. So we're going to get something that looks like that and that. And then again, we're locating the foci relative to our origin. So my foci is based off of these C values. So F is going to be equal to, you see we moved left 1, and then we're going to add to that 3.6. That's F prime. Or that's F. Our F prime will be -1 minus 3.6. Oh, wait a second. I think I'm on the wrong. That should be positive 1, right? We're vertical axis. There we go. So my foci is going to be a 0 C value, because my transverse axis is up and down versus right and left. All right, so we get, in terms of the y type of the coordinate here, we get a 4.6. What's the x? The x is the -1 that we've shifted. That's our h value. Over here, we have a 1 minus, so that's a -2.6 and a -1. So there's our F and our F prime foci relative, again, to our original axis. There's our graph. All right. By the way, find the equations of conics involve doing the reverse of what we just did. So find the equation of an ellipse with the foci on the line x equal 4. Has a minor axis on the line of y equal -3. And what's the length of the major axis? It's given as 8. The length of the minor axis is 4. All right. Maybe a little sketch to kind of see what's been described here. Here's our normal xy plane. And we have this line x equal 4 over here. And a line y equal -3 right there. And our foci is on this line, x equal 4. And our minor axis is on the line y equal -3. So I know my graph is going to look something like that. And we're supposed to be finding the equation of this thing. Okay, what can we pull out of this? Well, foci on the line x equal 4. Okay, let's start with just our generic ellipse equation. A squared, b squared equal 1. And then we ask ourselves, is that really the right one? If our foci is on an x equal line, that's a vertical line. That would mean our major axis is a vertical axis of x equal 4. So that means we put our a value where our y is. So this is going to be a b squared and an a squared type situation. What else do we know? We have a minor axis on the line y equals 3. Okay? We don't know how long it is, we just know it's there. So where these two lines intersect, our foci line and our minor axis line, which happens to be right there, that is the new center of my ellipse, which is going to be 4, -3, and that is your h k value. Okay. So where those two lines meet. The length of the major axis is 8, the length of the minor axis is 4. Okay, let's see what we can do with that stuff. So length of the major axis, we know is 2a, and that's equal to 8. So that means our a is 4. Length minor axis is 2b. That means our b is equal to a 2. Okay, so we've got our a, we have our b, which means we can find our a squared and our b squared. We knew that our foci line and our minor axis line intersect each other at the middle, at the center. And I think that is enough for us to be able to write the equation here. So we're going to follow this setup. For a translated ellipse that has its transverse axis on the y-axis, we're looking to fill that equation in with our hk's and our a's and b's. So 8x minus 4 quantity squared over 2 squared plus y plus 3, because you're y minus a negative 3, squared over 4 squared is 16 is equal to 1. So that would be the equation given that information of an ellipse. So the little sketch is helpful to kind of get a visual of what's going on here. All right, and then our last one, find the equation of a hyperbola. All right, so maybe we start out knowing it's one of these forms. That'll look like one of those guys. Vertices. Remember, the vertices lie on the transverse axis. Okay, so if the vertices are on the line y equal negative 2, that means my transverse axis is my is horizontal. So we know that our transverse axis is horizontal. Which means we know we're using that equation right there. Conjugate axis is on the line x equals 3, vertical. And just like for an ellipse, where you have a conjugate and a transverse crossing one another, guess what that is? So we have y equal negative 2, x equals 3. There is the center for where this ellipse is, or this hyperbola is going to be built from. So there's my hk. So the transverse axis and vertical axis combinations help me create h's and k's. Length of the transverse axis. So we know that 2a is equal to 4, which again, a is 2. Conjugate axis, 2b is equal to 6, b is equal to 3. We're ready to go. We've got everything we need, a, b, h, k. So we would say x minus 3 squared minus y plus 2 squared. A squared is going to be a 4. B squared is going